I'm actually thrilled to be here. So I've been working on the area of sensitivity analysis for a few years, and I started learning about this topic by books and papers published by researchers working in this institute. So I don't think it's easy to talk about sensitivity analysis here, but I'll do my best really. I'm thrilled to be here, and I'm going to give a presentation for 14 minutes or so. It's up to you. You might stop me if you want to make some discussion along the way, or you might keep your discussion or Q&A to the end. So, first of all, I'd like to thank my colleagues who've been working on this topic for the past 2-3 years or so. Oshin Gupta first, who basically worked on this idea of VARS with me since its inception, and we are still actively working with each other on this topic. And Amin Haknagahtar, who is here with me, and Razi Sheikhul Islami, and these guys joined me along the way, and so now we have a small group working on this topic at the University of Saskatchewan. And my apologies in advance if some of the materials I'm presenting are too basic. So many of us deal with models, different types of models, and these models have, receive some inputs like parameters, forcing, boundary conditions, and so on, and then respond to those to different variables or model performance metrics. And we can typically represent what's going on with the functioning of the model by some response function. So Z might be a scalar value or a vector, which is the response of the model as a function of thetas, theta 1 through theta n, different model parameters, let's say. And the model behavior can be geometrically represented by response surfaces, and there's theta 1 and theta 2. So this is a simple three-dimensional case. We could visualize it, but in high-dimensional space, no way for visualization. And sensitivity analysis can be very helpful then to help us characterize the influence of different parameters on the model response, and to, for example, derive some metrics for global sensitivity. So, sensitivity analysis. There's a clear definition for sensitivity when you talk about local sensitivity around a nominal point in the parameter space. So if we pick a point in the response surface and we take partial derivatives, which is essentially the slope of the response surface along the direction of the parameters, we get some clear definition of sensitivity, which is basically making sense in optimization sense or cost-benefit analysis around the optimal solution. And also, by second-order derivative, we can speak about the interaction effect at that given point. So this is good, a clear definition, but the problem is it's conditioned on a nominal point. And of course, if you vary the point across the space, the sensitivity information, the sensitivity assessment might be different. And overall, local sensitivity analysis, this kind of practice provides only a limited view of the sensitivity of the response surface to parameters or inputs. So we frequently need to globalize that kind of approach and derive some metrics or characterize the entire response surface. So probably the most intuitive way of globalization is to do that local sensitivity analysis, but instead of doing that at one point, doing it at many different points, and then we are effectively dealing with probability distributions of partial derivatives with respect to parameters. Then we need to derive some metrics. So first and second moments of these distributions are typically being used for global sensitivity analysis under this umbrella of derivative-based approach. So method of Morris or future extensions to that are all following this kind of philosophy. One problem here is that the response or the PDF functions of the derivatives of even such a simple function might be quite complex. These are actual PDF functions of the partial derivatives of this response surface, and while in practice we typically assume they are bell-shaped like this, the first two moments are enough, while in reality they might not be sufficient to describe what we are looking for. The other very commonly used approach is the variance-based approach, and that's based on the recognition that the response surface could be described by a PDF function. So if I throw in thousands of points around across the parameter space and evaluate all the z values and derive the PDF function, so I'm looking at something like this. So probability density versus this z with the variance of the function. Now the question in this approach is that how we can decompose the total variance to its constituent factors. Theta 1 and theta 2, how much of it comes from theta 1 and how much comes from theta 2. So if I knew the true value of theta 1 and it was here, then I could fix it at this true value, right? Then I could reduce the two-dimensional parameter space to a cross-section, and by doing that I could derive a conditional PDF function. So my original or total PDF function could be reduced to this one. And then I have a conditional variance. So this is conditional on theta 1 equals to this number. So by doing this, I'm reducing the variance. So the change in variance, or the difference between total variance and this conditional variance, is telling me how much would be the reduction in this case in uncertainty in z if I know the true value of theta 1 here. But the problem is we don't know the true value of theta 1. But what we could do, we could repeat the same experiment for different values of theta 1, right? And come up with different conditional PDF functions. And for each, we have a different reduced variance. And it's not that we are all the time reducing the variance. For example, in this case, by fixing the theta 1 at this point, by adding certainty to the problem, we are increasing the variance. So there's a paradox here. By adding certainty, I'm increasing the uncertainty of the model response. Anyhow, by averaging, now the change in variance for different locations, we come up with main effect of the variance-based approach. So these are sort of basic definitions of the two probably most commonly used approaches in the literature: derivative-based approach and variance-based approach. And again, like the derivative-based approach, although we assume all these distributions have normal, bell-shaped, nice shapes, in reality, they can have quite complex forms, and the variance of second order might not be sufficient to describe what we're looking for. These are the actual PDF functions for this. With that intro, I'd like to raise two major challenges in the literature around the idea of global sensitivity analysis. So local sensitivity analysis has a clear definition, but as soon as we generalize or globalize that to global sensitivity analysis, there might be challenges. First one being ambiguous definition of global sensitivity, meaning different methods, like the one I showed, are based on different philosophies for sensitivity analysis, and that's why they lead you to different, sometimes conflicting assessments of global sensitivity. And the second one being computational inefficiency, meaning you need to run your model many times to converge, to get stable, robust assessment of sensitivity. And in some real-world applications, models are computation intensive, and this kind of practice might be computationally prohibitive. So this is the discussion in this paper published 2 years ago, I guess, in WRR with Hoshin Gupta. And what do we mean by sensitivity analysis? Where do we look into these kind of issues? Just to clarify what I mean by ambiguous definition, I'm giving two simple examples here, and any of you can come with me here. So suppose we have a simple model with this ridiculous response surface, two parameters again, theta 1 and theta 2, and if I take the cross sections, you see those, and there is no interaction effect, meaning that the additive effect of the two functions along the two directions forms the modular response. Now, I'd like you to think of, so as a modeler, if you're asked which one is most sensitive, or which parameter, theta 1 or theta 2, have more impact on Z, which one you choose? Just think about it for a second. So you have the response surface, you have a model with response surface like this, you have two parameters, and you want to pick the more important one. One response surface or one direction is a quadratic smooth form like this, the other one is basically the mirror of the other one broken at this point. Any idea here? Which one do you choose as a modeler or expert in your modeling area? Any comments, any suggestion?
Well, I would say it would depend a lot on the context and on your knowledge area of the subject. And here, so I would say a priori, it's very hard to say, to answer that. That's my point of view.
Well, that's a very good point. So it's context dependent, right? That's, I guess, what you're suggesting. Any other idea? So I've been asking this question a lot, many different places, and people come up with different ideas. And interestingly, even us as experts in the area do not have a common definition or understanding in our minds about the sensitivity, but probably that's a very good explanation. Also depends on the context. For example, context is optimization, and you want to maximize the response surface. I don't know, you might say the blue one. But different people might have different ideas. But what we do in reality, we just apply the methods. For example, we apply derivative-based methods and variance-based methods, and both would tell you that they are equally sensitive. So for derivative-based approach, because the average derivative of the two functions are the same in the two methods, and for the variance-based approach also, the variance of the two functions are the same. So the two methods are telling me that they are equally sensitive, but obviously they have two different forms. So the form of the response surface is quite different in one direction versus the other. So that's being ignored, that these are two different functions. So a second example. Now, in one direction I still have that nice quadratic function, but in the other one I keep that dominant mode but add fluctuations. Now which one is more sensitive?
Suppose you'd say C2 because you would expect a small change in C2 to make a larger change in the output. Even though I guess you're probably going to say they put the same sensitivity in C2. But I don't know.
So William is suggesting blue is more sensitive because probably by perturbing, I guess, theta 2, you get more change probably.
Yeah, if even small changes are going to be...
Yeah.
Wow.
Any other idea? No one is suggesting C1?
It is more intuitive.
Daniel, yeah.
There's no rule. We have a feeling that C2 has a major impact, but why? It's difficult to say.
Right, yeah, it's very intuitive also. And again, probably context dependent. So let's carry on. If you apply the two methods, what we would see? Derivative-based approach agrees with William. So C2 is significantly more sensitive than C1 because obviously the slope everywhere tends to be significantly higher than the slope in the red. But if you apply variance-based approach, they are equally sensitive. The two functions have exact same variance. So this is one example of how they could be conflicting, and probably none of them are the best representative of our intuition about sensitivity. So we looked at these two examples, and here is the third one. I don't have a 3D surface of this to show, but again, this is a two-dimensional case, theta 1 and theta 2, blue and red. Any idea which one is more sensitive here? And I guess I have the answers of the two. So derivative-based approach telling me the two are equally sensitive, and that's obvious because the slope of the two, absolute slope, is the same. So we have the same slope everywhere, but the variance-based approach, S1 or red, is significantly more sensitive, and because it's covering a larger range of Z. So these three examples show how the two dominant approaches in the literature can be conflicting. And if you look deeper, what's being ignored in any of these assessments is the response surface structure. So here the structure was different in the two, it was ignored. Here you have a clear sinusoidal form. It's not shown really in any of these, and so on. And you know what? So these were simple examples, and in reality you might see significantly more complex response surfaces. These are examples of 45 parameter land surface hydrology model we have developed in Canada, and these are just subspace samples of the original 45 dimensions for two different parameters, and you see a range of behavior. And also, these features that you see can be different when you zoom in and zoom out, meaning when you look at different scales. For example, this area, which looked quite smooth, if you zoom in, you might see a lot of roughness, small-scale fluctuations, due to numerical implementation in the model and so on. So, of interest is really to take into account all the features from small-scale features to large-scale or dominant modes like this into account. So that would be the ideal, probably, means for sensitivity analysis. So I talked about these two approaches, derivative-based and variance-based approach. And now I want to explain what we have done, the so-called variogram-based approach, something we refer to as VARS. So we dig into the problem, and we tried basically to address those challenges I mentioned to some extent. This is not a perfect approach, but this is just, this is just a new approach that encompasses the two existing ones. And I'm going to explain what I mean by encompassing. So here is VARS. VARS stands for Variogram Analysis of Response Surfaces. What I tried to say in the previous slide is that a major weakness of the previous approaches is that none of them considers or take into account specially ordered the structure of the response of the Z value in the parameter space. In other words, they ignore the fact that the response values are not randomly distributed through the parameter space. So first of all, in VARS, we want to see the response surface structure directly. And also, unlike the previous approaches, VARS is based on the recognition that there is a spatially continuous correlation structure in the parameter space. It's not a random field. And also, the same applies to the derivative information of the response surface. And to address this, we basically use the concept of directional variogram and variograms and covariograms. And this is anisotropic variograms and covariograms. So, as you might know, when you want to deal with variograms, you have to deal with pairs of points rather than individual points on the response surface. So if I get two points, point A and point B, this forms a pair, and I have response values for the 2 points, and these 2 points are apart. and the distance between the two is characterized by vector h. So with ordinates h1 along the parameter θ1 and h2 along the parameter θ2. So I have two response values for 2 points that are this much apart, characterized by vector h. So we can derive the variogram and covariograph function basically for any response surface. Let's look at the variogram function and what it tells us. So this is the general equation for variogram, right? Variogram is the variance of change in the response surface as a function of h, distance. So this is variance, right? This is integration over the entire parameter space, integration over theta basically, and this h is the argument in the function. So this is a variance of change as a function of h. And so as I said, this is anisotropic variogram, meaning that it is different at different directions, and what we can do, we can extract the directional variograms out of this variogram function. So at different directions, then we get different variograms. For an n-dimensional problem, we get n-dimensional variograms. And so these variograms are functions of h, as I said. We would refer to this h as perturbation scale in the parameter space. So variogram is variance as a function of scale. Covariograph function is pretty similar, but instead of being the variance of change, this is the covariance of points as a function of distance. So we use these two concepts to build the VARS methodology. Let's go back to the example 1. So my response surface again, and now the variogram surface. And as I said, this is anisotropic, meaning in different directions you get different forms of variograms. So if you take the directional variograms out, you would see this. So gamma is the variogram as a function of h1 and h2. So what do we see here? As I said, variogram is variance of change as a function of scale, right? Far to the left, for small h values, the two functions are similar. And this is consistent with what we've seen with the derivative-based approach. Equal sensitivity and derivative-based approach. And far to the right, for large perturbation scales, again, the variance of change converge. So the two become similar, and this is now consistent with the Sobol approach, variance-based approach. So the two endpoints are telling me about the two common approaches, derivative and variance-based approach, and in between, everywhere, the blue one is higher. So how do we interpret this in terms of sensitivity? It all boils down to the definition of variograms, which is the rate of variability of the response in the direction of parameter I at the scale of h. And the fact that this rate of variability is changing for different scale values, it tells me that sensitivity is a scale-dependent concept. So by scale, I mean perturbation scale. Let's move on to the second example. Here is the variogram surface and directional variograms. So the first thing to notice is that variogram reflects the structure of the response surface. So you see multimodality here and there. Now far to the left, blue is significantly higher than the red. So this is consistent with the derivative-based approach, right? Because the slopes are significantly higher for the blue. And far to the right, they converge again. So dominant mode in the large scale, dominant variability of the two are the same, right? And that's why for large perturbation scale, the two have or show the same rate of variability. And again, everywhere in between, they are different. So what I'm trying to say is that the variogram function is a representation of the spectrum of information on sensitivity across the full range of perturbation scales. But for real-world applications, we need to come up with a metric, right? A metric that practitioners could be using as a global metric for sensitivity. So to derive that metric, use the concept of integrated variograms. To basically integrate the variograms, and this is, as I said, because there may not be a single perturbation scale that reflects the entire intuitive understanding of sensitivity. So we may need to look at the entire spectrum of scales, and that's why we either have to look at the entire variogram and make a comment, or come up with an intelligent way of combining everything into a single index. So this variogram integration is simple. I have the gamma function. This is my variogram. Now I'm integrating that over h from 0 to some big H. So this is my directional variogram of example 1. If I do the integration, I will see these functions. So obviously, as I go from 0 to 1, the blue one gets higher and higher, telling me that the blue one is more sensitive according to this metric. So to have a global metric for sensitivity analysis, just to recap, we do variogram integration, and variogram integration is equivalent to taking the area under the curves, right? So, for example, this point at the end corresponds to the area under the two curves, right? And the blue one is obviously significantly higher. So this is a metric that we define called VARS, which stands for integrated variograms across a range of scales. And for this range of scales, of course, we can have different ranges from 0 to capital H. This could be anything. So if this H is 50% of the parameter range, I would call it IVARS 50. If it's 10% of the parameter range, I would call it IVARS 10, and so on. And this is basically my metric or global metric for sensitivity. A new example. So I'm carrying on to a higher dimensional problem, a response surface with 6 parameters. So I'm defining a mathematical function, y, as a function of 6 subfunctions, g1 to g6, and there is no interaction effect. The 3 functions are being added together to form the y. And here I'm showing the 6 functions. So first, let's look at y1 and y2, blue and red, and I'd just like you to think about which one is more sensitive if you were to choose one of these two. And obviously these two are more sensitive than the rest of the parameters. Also look at y3 and y4. Not sure how much this is visible from the back, but I4 is a green line, a smooth green line under this black line, and y3 has the same dominant mode with a lot of small scale fluctuations. So y5 is here, not very much visible, and y6 not at all visible, but it's a flat line. So y6 is fully insensitive. So your sensitivity analysis should tell you this. That doesn't have any impact on the model response. So I have the 6 parameters, and if I apply VARS, I get this directional variograms. So again, let's compare y1 versus y2, blue versus red. So early on, the blue one is higher because for small-scale perturbations, obviously the red one is more dominant, but at some point it crosses the red one. So at some point the red one becomes more dominant. And this is for larger scale changes in the parameters. And of course, again, if you think about it, if you want to have if you want to go with smaller scale changes like this, the blue one might have more effect than the red one. But for larger scale perturbations, the red one might be more significantly contributing to Z. And now compare y3 and y4. So one is a smooth function, and the other one is the same, just augmented by some sinusoidal noise. And here, the noisy one is this black, and the green one is going like that. So for small scale perturbations, the black is significantly higher. And this is on a log scale, huh? This is on a log scale. And green is less sensitive, but when we move to the right for larger H values, the two converge. So the dominant mode for larger scales of the two functions are similar. And that's why when we go far to the right, they look pretty similar. So this yellow one, y5, is here obviously less sensitive than the other ones everywhere across the perturbation scale. And y6, the fully insensitive one, I guess light blue, not visible here, goes 0. So the variogram of the last one is like this. Just going 0, 0 effect for any perturbation scale. And in variogram analysis, we only interpret half of the parameter space. So this relates to variogram concept, not VARS itself. But just to explain this, my parameter range is between 0 to 1. So basically, my H value then should be between 0 to 1. This is because H is distance. But when it comes to interpretation of variograms, generally we only look at half of the distance of less than half of the range, because beyond that variogram loses its meaning. And here is my integrated variograms. Again, I'm ignoring the last half. So this is the metric I defined earlier, IVARS 50, this is IVARS 30, and this is IVARS 10. So I said 10% of the parameter space, 30% of parameter space, 50% of parameter space. And these metrics could be used directly as a metric for global sensitivity. More practical example, again, a very simple rainfall runoff model with 5 parameters. This model is called HIMOD. Some of you might be familiar with it. This is a simple toy model for hydrology, having 5 parameters. If we apply the method of Morris or derivative-based approach, we get this kind of characterization. Cmax is the dominant one, followed by RQ, and this alpha and basically E exponential are equally sensitive. And if we use the other approach, variance-based approach, I get a different assessment. Now RQ is more sensitive than Cmax, and now alpha is 6 times more sensitive than E exponential, while here the two were similar. And if we apply VARS, we get this, again, directional variograms. So now Cmax and RQ, the two sensitive ones, cross at this point. So early on, for smaller perturbation scales, red is higher, but as you move on, blue becomes more significant. And alpha and B exponential, early on, they are equally sensitive, but for larger values, they diverge. So what I'm showing you is exactly the same as the Morris derivative-based approach is for far to the left, and Sobol is far to the right, consistent with the two. And basically, VARS now generates a spectrum of information across the parameter perturbation scale and all, and you can also derive integrated variograms to have a metric like IVARS 5 here now or IVARS 15. So I mentioned through examples, I showed how VARS could produce derivative-based and variance-based approaches results also. But there is actually a clear theoretical relationships between these three. Here I'm telling you how. So this is a conceptual variogram function here, right? Gamma as a function of h, and this red is covariogram function. And covariogram function is typically similar to, close to the mirror of the variogram function, but with some differences, and the differences will have a lot of information useful for sensitivity analysis. For small h values, we can theoretically show that when we go to the left, we can theoretically show that gamma, or the variogram value, is proportional to the variance of derivative information, or the expected value of the squared derivative. These two metrics have been used in the derivative-based approach as metrics for global sensitivity. And if we go far to the right, for large h values, this is definition of variograms. For large h values, you get to a seal in variograms, and at that seal, the value of gamma is close to the variance of the stochastic process underlying the model response. So now the relationship with the variance-based approach becomes clear, and with some mathematical manipulations, we can derive Sobol total order effect out of the variogram and covariogram equations. And the mathematical proofs of these are available in the papers, but the point I'm trying to make is that once you apply VARS, it generates the full spectrum with its own metrics, but as side products, it also generates the elementary effects and total order effects. And this is, we tend to show its functioning. So VARS generates a spectrum of information on sensitivity, while as limiting cases it reduces to Morris and Sobol. These are my limiting cases, basically. Okay, so I've talked about the theory of VARS. William, how am I doing with time? Okay, thank you. So like any other concept to do sampling, right? So far, what I've shown mostly was by directly or analytically deriving the equations, but you need to take samples. And to do that, we developed a sampling algorithm called star-based sampling, and collectively and so how it works is quite simple. It's a randomized structured sampling. Suppose I have a three-dimensional parameter space, x1, x2, and x3. So first, we randomly sample star centers. For example, like through Latin Hypercube sampling, I'm taking 2 star centers. And then I take samples structured along the length of these 2 stars. So by this type of sampling, I can derive directional variograms, derivative-based sensitivity measures, and variance-based total order effect. So this sampling can basically feed fully to VARS to generate all these metrics. And again, so the computational cost of this sampling is can be calculated by this equation. So I'm approaching the end of my presentation. I'm not showing any more case studies, but we've applied VARS to different case studies, and we have compared it to different other GSA robustness analysis implementations, and we've seen VARS is significantly more efficient and robust. 1 to 2 orders of magnitudes across different case studies. So we've been looking at the reasons for that, and it could be explained probably by this argument that VARS is very efficient because it's partly based on information contained in the pairs of points rather than individual points. And as you know, you can easily collect many pairs in a parameter space. For example, when you have only two parameters, parameter 1 and parameter 2, with 5 points, you collect 10 pairs, right? And by adding just one more point, you collect 5 more pairs. So geometrically, the number of pairs geometrically increases by increasing the number of points. In other words, the rate of increase in the pairs is n squared, then n is the rate of increase of points. And here's examples. For 1,000 pairs, you get 500,000 points. You get 100,000 pairs. And just by doubling that, you get close to 2 million pairs. So this has been some ongoing research in our university, and so we've implemented everything in a MATLAB package so far that was released last year called VARS tool. This is the website for that, and a short video which is basically what I presented here, and here's a snapshot of the user manual. So we are now working on other versions like in Python and R for users that are more comfortable with other programming languages. In one minute, I just like to add this. So we've recently added this capability to VARS, which is called Progressive Latin Hypercube Sampling. So as you know, in this kind of sampling-based analysis, you have to generate a sample, and you need to know the size of your sample a priori. Typically, for example, when you run Latin Hypercube sampling, you need to know how many samples you want to take, and you have to generate it all at once to make sure you preserve the Latin Hypercube properties. But in practice, it doesn't work always. You go, for example, 10,000, you run your model, and you realize your algorithm hasn't stabilized yet, hasn't converged, you need to go more. Then you have to go back and resample again, and then you lose your distributional properties of interest. And there are, of course, other approaches for sequential sampling, like Sobol sequence. But here, we try to add this capability to make it like a Hypercube sample. You generate your sample progressively while preserving the distributional properties of interest. So with these graphics, I'm trying to show how it works. Basically, you go by slices. So this is my progressive sample size, 2, 4, 6, 8, and so on. This algorithm generates slice 1, which is obviously a Latin Hypercube. And then it generates slice 2, and now the union of slice 1 and slice 2 is Latin Hypercube. Then the algorithm generates a new slice, again the union of these remain Latin Hypercube, and so on. So this way you can increase the efficiency and the convergence rate of your algorithm. So this is also implemented now in VARS tool. And so this is something Amin is going to be talking about on parameter perturbation skills that I've just discussed, but Amin looked more deeply into the problem across many cases. I'm going to also advertise a bit about our center and who we are, what we do, just 2-3 slides, I guess. So I'm coming from Global Institute for Water Security at University of Saskatchewan. So my affiliation is School of Environmental Sustainability and Department of Civil Engineering, but I see in this global, which is at the heart of the university. So it's not an academic unit. We've been hired to academic units, but work at the institute. So we are in Canada, of course, located in Saskatchewan, city of Saskatoon, and we are housed at the National Hydrology Research Center. And that's a picture of a group of us there. Of course, our website includes all the information needed. And my lab is a lab inside the Global Institute for Water Security, and this is basically my website. So research and everything, software, for example, more tool is available there. And just our history, we are relatively new. So University of Saskatchewan has had a legacy of water research really for decades, but at 2010, there was a big momentum to increase this kind of research in Canada. We were established Canada Excellence Researcher in water security with 30 million fund. 1 year later, Global Institute for Water Security launched with 7 core faculty members. I'm one of those, and basically this institute created a network of water researchers across university and Canada. 2013, it was the beginning of a new journey, changing whole region research project covering Western Canada, and just recently we launched this new program, Global Water Futures, Solutions to Water Threats in an Area of Global Change. This is a very big program, $77 million coming from the federal government, and with total cash support from 4 partner universities. It totals $144 million. So we are still at the beginning of this new program, and we are actively working with others, and we are very interested in extending collaborations with well-known institutions like yours. Here's a map of our current international and national partners, and this is something we've been discussing for people for some time, and we are very much interested to really work with you. And I leave it here. Thanks very much.
Oh, because you start from a multivariate function, so how do you get this function? Is something that is empirical related to the variables, or first you model this multivariate and then you take the conditional distribution, the variogram and whatever? Do you have a method to model?
So what I've showed is that a priori we assume there's no correlation and all parameters are uniformly distributed.
Okay.
So we deal with a multivariate distribution, but a simple one, a fully uninformed, no correlation, uniform distribution. But the theory could be applied, I guess, to more rigorous multivariate distribution, normal, for example, with correlation, but we haven't done that yet.
But so just to understand, so first you make all the variables independent. So you move in a hyperspace with
I'm unclear about this question a bit. I'm not
No,
sure.
but anyway, maybe we can
assume that
discuss
they're
later.
independent. The assumption is that they're already independent. You
Okay.
don't transform.
So
That's
okay,
what
you
you can
assume that they are independent. Okay.
Rigorous questions.
So you cannot apply two dependent set of variables, or can you apply this method to a dependent set of variables?
I guess if you know a priori that two parameters, for example, are highly correlated, your assessment of sensitivity might be biased.
Okay.
And
You can move in an hyperspace
of
with
course. I mean,
rotation
yeah.
That's
That's a very, very good point. So I'm coming from hydrology background, right? In my area, I mean, you're talking far ahead of people in my area.
Okay.
I mean, we don't, of course, as I said, we know many of our parameters, as I said, hydroconductivity versus porosity of soil, highly correlated, but in these kind of analysis, we assume they are not. And that could bias our results. But, so this follows the mainstream, but, I mean, that's something to take into account, of course.
May I ask you, after the presentation, in my opinion, what I see, it's a similarity between the integrated variogram as a function and the component from the hard transform dealing with the cumulative energy. So the same way, like you have defined VARS, because you can assign them arbitrary by making the step function 10, 20, 30%. In hard, I find exactly the same procedure when coding the information about the pairs by saying to define the amount of energy we wish to retain and to identify those elements in the vector that produce that energy. And you assume that the producers of energy, which will be reflected by integrated variograms, are equivalent and uniformly distributed. in probability at less. Have you considered the non-uniform distribution of energy contributors?
Let me make sure I understand your question. So you use analogy to energy function.
Well, you use the information. What you are trying to do by introducing the method of integrated variograms is to encode the information about pairs. That means amplitude and frequency modulation in both. And this is the wavelet transform. And the simplest one is the Haar transform. By coding the information about both the variability in magnitudes and in one dimension and variability in another dimension, H1 and H2, you start from the possibility that both out of them are independent, uniform or non-uniform. In order to do this transform, you should assume that the energy contributors, because you are constructing the dot product, H1 per H2, the energy integral that you will get as the output is dependent on how two dimensions are varying. So the information about H1 and H2 are not mutually dependent or not mutually dependent. So you need this knowledge. Where this knowledge is encoded, you lose it.
Right. I don't think I'm looking at what you're talking about. Is it related to the question here? You know, yeah, I'm still unsure if I understand your question fully, but as I said, we are assuming that parameters are uncorrelated a priori, and we're only looking at the interaction effect, which is a result of the response surface. I'm not sure. I mean, do you have something to add there?
No, this, the assumption would be they're uniformly distributed, independent, and then we'll go from there. Nothing more complex than that at this point, at least. Okay. Yeah, this is...
You know what, but that is something I guess we might discuss offline. I mean, I need to learn what exactly we're talking about. It might be a good addition in the next step for us to do.
Yes. Could be, yes. Yeah. Because it's come from information theory, so when you encode the information from two variables, it's clear that you are reducing, but this coding is losing.
Right.
And consequently, if you have no information about the rate of variability of the information, not about the parameters, but information, you are losing. But when you exploit the finite innovation rate in the information, you are losing less. So
the only
you
thing
can conserve the information. So basically, by reducing, resulting integral obviously is simpler, but it is not said that it will be performing. So
the only thing I would say that is kind of expert judgment comes into play in defining the variables that are at least softly independent. When, like in a hydrologic model application, we use our expert knowledge in terms of the information context. If you wish to kind of make the variables or the parameters we want to assess their sensitivity as independent as possible. So if we knew a priori they're highly correlated or highly dependent, you kind of put one aside and use, so probably just softly expert knowledge a little bit, but not rigorously like theoretically as you mentioned.
I got your point, thank you, because you are doing the Huffman coding based on the prior knowledge about the model, the phenomenon, so your model dependent in this way, because you infer the limited variability because of the model.
Okay. So, thank you very much.
Okay, so, like I said, if anyone wants to just grab a bottle of water, coffee or brioche now, and then we can start again in 5 minutes.